Podcast Topic 1, Lesson 2, the first part. Then this podcast will be talking about the phases of matter, phase changes, and the energy that's involved in going through that phase change. Now there are 3 different phases of matter. Actually, there's 4 different phases of matter. There's solid, liquid, gas, and the 4th one being plasma. But in high school chemistry, we don't normally take the time to go over plasma, and we won't be in this chemistry class as well. So we'll be focusing on just a solid, liquid, and gas phase. The nature of a substance determines the phase in which that substance will exist under normal conditions, such as like normal room temperature, which is 23 degrees Celsius. It's about 72-ish Fahrenheit. Gold, for example, because of its properties, and it's going to be a solid at that room temperature, whereas water, H2O, is going to be, because of its properties, is going to be a liquid at room temperature, whereas oxygen in no way, shape, or form could be either solid or a liquid at room temperature. It is going to be a gas at room temperature. So it's all relative when we look at this to temperature and what those temperatures are, as well as pressure, and we'll be discussing that a little bit later as well. Now for these next few slides, I'll be talking about the differences between a solid, a liquid, and a gas. And you will be doing a phase simulation in class to help you to visualize this and to reinforce the information that you're going to be receiving in this podcast. But I, again, definitely want to make sure that you are writing down notes and writing down any questions that you have based on the information that's given in the podcast. At the end of us talking about what a solid, a liquid, and a gas looks like, you'll see that I'm comparing them with the same properties throughout. So you might want to then make a data table of those properties and enter each property, tell me what is it for a solid, a liquid, or a gas. So again, rearranging your notes possibly in a graphic organizer like we did with the concept map would be a great tool to help you to reinforce the information. But let's talk about solids first. So solids have a definite blank and blank. And let's see if you can think about right now what it might be. They have definite volume. I'm just going to abbreviate. And they have a definite shape, which makes sense, guys. Seriously, if you're thinking about something that is a solid, you can, if it's like a square, obviously you can take its volume, length times width times height. If it's not a regular object, we'll do the displacement method like we did before when we were trying to figure out the density. You had to figure out its volume. But its volume is going to be how much space it takes up. In solids, it doesn't matter whether temperature or pressure, it takes up the same amount of space. And it will take, it'll keep its shape. You really, with a solid, you can't like change its shape. You can't compress it or draw it back out. The particles are arranged in a crystallized manner. Let's see, I think I can. So hard to write on here, but it's in a crystallized manner or a regular geometric pattern. I guess that's the key that you want to write down. It's a geometric pattern, and I'll be showing you a video which kind of describes or shows this, but again, referring back to your phase simulation, you'll be able to see that as well. So it's geometric, it's very organized, it's very nicely, neatly packed together. In terms of their movement, well, they move by vibrating around each other. So they don't really slide past each other, they don't move from one place to another. They kind of stay packed together, and they kind of like just move back and forth, and maybe can like vibrate just a little bit. And I'm going to talk about a hula hoop experiment that one of last year's students did when they were teaching the little kids about solids, liquids, and gases, and it was a great tool that they used, and I'll describe that at the end to again describe solids, liquids, and gases. In terms of their force, because solids vibrate and they don't go from, if you're next to one molecule, in the next second you're going to be next to the same molecule. You're going to vibrate, but you're not going to go past them and move to a different molecule. So what happens is that they have very attractive forces, and because they are attractive, that's why they don't move past each other. They can't get past each other because they are attracted to that molecule, and therefore that holds them together. So they have very attractive forces, and they cannot be compressed. They cannot be compressed. So you can't squeeze them. So you just can't squeeze. All right, so now let's go on to liquid. Again, I'm going to talk about the same things. They have a definite something, but not a definite something else. So in the past, we were talking about shape and volume. So do liquids have a definite shape? Well, if you think about it, if I have water, I can pour it into a coffee mug, a wine glass, a drinking glass. I can pour it into a bowl, and it's going to take the shape of that container. So it does not have a definite shape, but it does have a definite volume, because I don't care what I put it in, I'm still going to have the same amount of that water. It's not going anywhere. It's not getting smaller. It's not getting bigger. It's just taking up the shape. Its arrangement is not geometric. It is a little less organized than a solid. So let's just write down less organized. It's not completely disorganized, but it's less organized. It's not a neat up and down rows type of thing like a solid would be. The force of attraction is less than a solid, which is why it can take the shape of its container, but it is more than a gas, which is why it has its volume. It doesn't change in terms of getting further away from something or closer to something. Its movement, instead of just saying it vibrates, it actually can flow or slide. So that's what allows it to go ahead and take the shape of its container, because it's a little bit more flexible, and it can go and slide two molecules past the one that it was right next to. It can't go completely away from them, but it can slide a little bit. It has a little bit more flexibility. But even with that being said, it cannot be compressed as well. That's going to come very important when we talk about the gas laws. There are laws that go through gases just because of the fact that they are different. See, solids and liquids, they can't be compressed, but gases, they can be. And so when we get to the gas laws, you'll see that we're going to be able to do some math problems with that. We'll talk about airplanes, potato chips, and all that kind of stuff when we get there. So now going on to a gas. Gases, their volume is not definite, nor is their shape definite. You can't tell me exactly what the volume of a gas is unless you tell me its pressure and temperature under which it is we're talking about. So you know that because if you take a balloon and you blow it up, you take the measurement of it, you put it in the freezer. When you take it out, when you look at it in the freezer, it's going to be smaller because the gas is compressed. When you take that balloon and you put it over top of something that's hot, maybe like some steam or something, or you just take outside where it's really, really hot, it's going to get bigger, which is why you know that you can't have, can't heat up a container that has gas in it, because it will explode, because the gas needs to get bigger when the temperature goes up. So it doesn't have a definite volume, and it doesn't have a definite shape. I can put gas into anything, it's going to fill its container. The arrangement is very disorganized, very unorderly, it's very random. These gases, all the molecules in a gas have a mind of their own, and they don't care about anybody else that is also a gas, and they are just random. And therefore their movement is chaotic. It is very, 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 very all over the place. Very fast. The fastest, they're very, very fast because they're not attached to anybody, so they can move faster. And you think about a solid, which is really strongly attracted to another right next to it, that's not going to allow it to move because that person's attracted to the other person, which is attracted to the other person. So you got a big, long chain. You're not going to be able to move pretty fastly. With a liquid, you can move a little bit faster because you can go, you know, 2 or 3 down from where you used to be, but not like all over the place. Whereas a gas, they're individual molecules, and so they can go wherever they want to, whenever they want to, however fast they want to. They have nothing holding them down. They unhitched the plow and they just went. So they have fast movement, and their attractive force is very, very weak. That's why they can move all over the place. Now, in terms of phase changes, so we're talking about now, oops, don't want to do that. We're talking about now going from a solid to a liquid to a gas, or solid to gas, or just changing the phase, changing the form. It's a change in form, but not composition or formula. That's extremely important. So understand we're changing its form, whether it's moving fast or slow, whether it's taking shape or whether it's not. All those properties that we were just talking about, a solid, liquid, and gas, we're changing those, but we still have the same thing. We have the same formula. So because we have the same formula, but we've changed what it kind of looks like, or its form that it's in, this is a physical change. Remember from a couple of days ago, we talked about the difference between physical and chemical change. So it's a physical change, phase changes are. Phase change is dependent on a couple of things. Well, you tell me. In order for water to be a solid, a liquid, or a gas, what changes it from a solid to a liquid, or a liquid to a gas? Temperature. So phase something in is dependent on its temperature, but I can also make something that is a gas and make it into something that is solid, even though it doesn't want to, by cooling it down. And sometimes cooling it down just isn't enough. Sometimes I have to cool it, and I've got to squeeze it. So pressure is the other factor that phase is dependent upon. So dependent upon the temperature something is at and the pressure that it's under will depend upon what phase it's in. Remember, everything has a normal, like water's normal phase is a liquid, because we're talking about room temperature, and at room temperature and standard pressure, at standard atmospheric pressure, normal conditions, it's going to be a liquid. But I can change those conditions at any time and manipulate them, and I can make it go into a different phase. Now you're going to need to know all 6 phase changes, and they are in this diagram right here. Easy, melting to, solid to a liquid. You probably are going to want to write down everything that I'm saying here in terms of solid to a liquid. Evaporating is going from a liquid to a gas. Going backwards, we're going from a gas to a liquid, like when it rains. That's condensation. Or you see that on your glass when it's warm and there's a lot of warm air can hold a lot of moisture in it. But then when it hits the cold glass, cold can't hold moisture, so that gas becomes a liquid and it condenses. And then freezing is going from, obviously, a liquid to a solid. And then these other two are probably the new terms for you. And the solid going to straight to a gas, it skips the liquid phase, it doesn't melt at all, it goes straight from a solid to a gas. That's called sublimation. Dry ice, this is an example of it right here. Carbon dioxide and iodine are the 2 substances that I want you to know that readily sublime. They sublime. Not very many substances sublime. Or, let me say that. There's very small margin of error for them to sublime. So carbon dioxide and iodine are the most readily substances that sublime. Go straight from a solid to a gas. They do that as easy. The opposite is going from a gas straight to a solid. And an example of that would be frost. So you have this moisture in the air, and we see this. We have this moisture in the air. Again, it's warm, and then all of a sudden, and all this warm air holds all this water vapor, or all this water gas. and it's humid, and then all of a sudden it gets cold. Well, when that water, the air, touches something that's really, really cold, and it's under certain conditions, this is going to be happening in the fall, you will get a frost. And that's when you think it's snowed outside, but you see the little crystals, and it's not. It didn't snow. It didn't fall down that way. It actually hit it and instantly became a solid. So those are the phases. Oh, very important. This melting phase, or this melting phase change, is called fusion. F-U-S-I-O-N. And you need to know that fusion is a synonym for melting. Star it, write it down, you need to know that. Seems the opposite of what you would think, because when you fuse something, you put it together, and here you're melting, and so you're kind of like breaking it apart. So it is actually the opposite of what you think it should be, but it's not. Fusion. Fusion is melting. Please make sure that you write that down. And the last slide. Phase changes occur when there is a change in energy. So in order for you to go from a solid to a liquid or liquid to gas, there has to be some kind of energy change. Energy change is related to particle arrangement. So if you want to change the way particles are arranged, you have to change the energy. You either have to release energy or gain energy to go ahead and rearrange these particles. Now I'm going to put something down here, that a little mnemonic device that I use, and you'll use it throughout the course, because we'll be coming back to this later, but I use Mr. Ab. The reason why I use the Mr. Ab is because this M is going to stand for make bonds. Oh, you can't see that, but it should say bonds. Make bonds. And this break, or this B, stands for break bonds. So, and this R stands for release, and this A stands for absorb, which is the same thing as gain. My O's aren't doing very well here. Okay, so an exothermic phase change is when you release energy, right? Release energy, and therefore you must be making more bonds or putting things more together. So what I'm going to do right now is I'm going to ask you to think about the 6 phase changes that we just talked about over here, and decide which one of these phase changes is exothermic and endothermic. And in order to do so, what you should do is say, okay, are they making and putting more together, or are they breaking apart? And if you can tell which ones are making and breaking, you can tell which ones are releasing and absorbing. And that will give you your exo and your endo. So I'll give you a second to do that. Pause it, and then come back, and I'll talk about it. Okay, so I hope you did pause it and try to figure out. So let's take melting, for example. Melting is going from a solid to a liquid. Solid to liquid, going from regular geometric and packed together to less packed together. So you're breaking bonds. Breaking, if I keep my Mr. Ab up over here, breaking goes with absorbing, and absorbing means gaining. So we're saying melting is endothermic, because you're gaining, and endo means gain and exo means release. I forgot to maybe again mention, look at the beginning, look at the prefixes, like an endoskeleton from biology. Endo means inside. Exo, anything with an EX means outside, like exit is your way to go out. Exoskeleton is a skeleton on the outside, like a grasshopper or something like that. So take those, endo and exo. So anyways, melting, you're breaking. Breaking means absorbing. Absorbing means gaining, and therefore it goes in this column. Okay, so now let's take a look at something else. let's take a look at going from a gas straight to a solid. So gas straight to a solid. Now remember, going gas to solid means that you are depositing. It's called deposition. It's the opposite of sublimation. So a gas to a solid is deposition. So we're trying to figure out where deposition goes. Is it exothermic or is it endothermic? So solid, gas to a solid, looks like I'm making my bonds tighter. Make stands for release. Release means exo, so I'm going to go ahead and put over here deposition. So I'm just going to go through one more, and then we'll in more detail, and then I'll just talk through the rest of them. So let's just say we're going from, let's say we're boiling. So we're going from a liquid to a gas. So liquid to gas. That looks like I'm breaking part because I'm getting less packed together, right? So break. I bring my Mr. Ab back up here. Mr. Ab. So break up, that means absorb. Absorb means gain. That means I'm endo. Therefore, I'm going to put boiling as an endothermic reaction. And let's just go ahead and talk about the other aspects. Well, what's the opposite of boiling? Condensing, right? And if you go through that as well, condensing means that you are putting it back together. You're making. Making means releasing. Releasing means exo. What's the opposite of melting? Freezing. Freezing, you are putting things back together, so you are making. Again, making means releasing, and that's why it's exothermic. And the opposite of deposition was sublimation. Again, sublimation is going from a solid straight to a gas. You are breaking, and breaking means absorbing, and that's endothermic. You need to know these, and you need to know how to explain why. I will discuss a few more examples and answer any questions you might have in class tomorrow. So, here we go.